It's my great to introduce Amit Patel from Colorado State University, who will be speaking to us on generalized persistence diagrams.
Right, thanks for having me. Thanks for listening. Okay, talk about generalized persistence diagrams. This is an archive right now. Figure out how to. There we go. Yeah. Focus on classical persistence. So the idea here is you have some constructible filtration of a space. So I like to think of functions. So filter a manifold by a Morse function. On this in real line, it's essentially finite, meaning the homotopy type changes at only finitely many values. And persistence we have requires computing homology over a field. So when we ignore all torsion in data, the mission here is to develop a theory of persistence where we study torsion in data. And so some of the core ideas in my Patel generalized persistence diagrams you can find on the site. Talk short and simple because I think core ideas are pretty simple. So I won't do it in this full generality. I'll just do examples here. This talk into Morse functions. So given some Morse function on a manifold X, we do iteration, and we apply analysis of homology using field coefficients and integer coefficients, and show how we can construct a persistence diagram for both, being the classical example. Introduce a new metric on persistence diagrams I call the inversion distance, and that says that if the two functions differ most epsilon, and the distance between diagrams differ by epsilon. Basic idea, you have some space and a Morse function on it. You do iteration. So on the left here, I'm homology with functions in a field K. So I'm using homology, and you get something like this. Here I have I'm filtering a Klein bottle here. And then if you see torsion, so you get a Z when you attach the first one handle. You get an copy of Z when you attach the second one handle. And then with cap, you get mod 2Z plus C going on. Theory of persistence tells us something about torsion in data. And you apply homology to it, it gives us something called a persistence module, which are from the real line with ordering less than equal to category C. And we're into categories for talk. The vector spaces, so vectors over some field K. The degenerative abelian groups, so if you compute a Z coefficients, this module valued in this thing, category of finite abelian groups. The idea here is a module computed using Z coefficients and apply a function as the free part. It'll give us a persistence module as valued in the category of finite abelian groups. So the idea present here only works for constructible persistence modules. So the idea here is in a constructible persistence module, things only change at a finite number of values. Definition, so this must be some finite set of real numbers, and a F is S constructible if Well, so f of p is 0 for all values of p less than s1. Two critical values, s1 and s2, you have and equal to q as an isomorphism whenever p is greater than the last n. This function or a finite filtration, you're going to get a constructible persistence module. Yeah.
Do you use vector spaces to be finite dimensional?
You want them to be finite dimensional. Yes.
Okay. Thanks.
Yeah. In fact, I want them to be the category of finite dimensional vector spaces over the field K. A diagram, so it's a plane, and you have a bunch of dots in the upper left-hand quadrant. Sorry, in the you're above the diagonal. So classically decorated with just multiplicity. So here's what I think about a persistence diagram. I define a post set EGM. So of all half-open intervals of the form R, so it's open on the right side, infinity. And then Ewing group G. I'll require partial ordering on this G, but I'll discuss that later. And so I diagram as a map P from this poem into some group, only finitely many intervals. So then this group G would be Z, because all the multiplicities are positive. Questions? So here's how Steiner, Edwardsburg, and Harrer define the persistence diagram. So this is in the setting of coefficient. So I've dropped the K here. So persistence module, a constructible persistence module that looks like this. So very simple. So we have things change 0, 2, 4, 6, and 8. I have so it's the two-dimensional vector space. A vector space over 4, the one-dimensional space over 6, and maps between. The diagram of this module, we'll call P sub F, satisfying the equation. So remember, is a map from DGM into, in this case, it's Z. Satisfy the following conditions. So if I take any point, any point in the diagram, P, it'll get left-hand quadrant determined by this point, and sum. So I'm sum over all containing PQ, and that is the rank of the image from P to just before Q, where delta is sufficiently small number. And so this is the following. I'm going to map from this post to Z as follows. For each interval PQ, I'm going to set the rank of the image from P just before, so there's a typo right there, just before Q. So this gives me BGM into the integers. Diagram inversion of this function df. So that for some I, a containing I. So the Mobius is think it's combinatorics, and there's a lot of work on this. It turns out the solution always exists, and it's unique. So in the formula works over not over just Z, but any abelian group. And so this allows us to generalize B vector spaces. Mobius inversion works. So here's our persistence module of vector spaces. And we have every BF. So there are many intervals, but since our module is constructible, we only care about finitely many of them. For each grid point, so 2, 4, but I get the rank of the image from just before 4, and it's 2 the same thing. So look at the image from 2 just before 6, it has rank 2. 6 and 4 to 8. So this is what I get. And I do a Mobius inversion persistence diagram. And the solution to the Mobius inversion is because DGM is such a simple poset, is very easy. So here's what it looks like. So what is the value of the persistence diagram at 2, 6? Well, I go to 6 in DF here, and I do the following sum. I draw a box. And plus 2 is the number of it, which is 0, plus the left of it, which is 0, minus the number below it, which is 0, and I get 2. So value at, what's the value of the persistence diagram at 4, 6? Well, the solution following, you take 3, so you go to DF, you look at 4, 6, you have 3 there, you put a box there. 3 minus 1 plus 0 minus 2, and you get 0. The diagram at 4, 8, well, you go to DF, 4, 8, you put your box there, and you do the sum. So minus 0 plus 0 minus 0, just 1. Very simple. So you can, the solution to the Mobius inversion formula is that this is exactly how the persistence term was defined by Hohenstetter and Harris.
So
yeah.
That minus thing, is that called the Mobius function?
Yeah, this function on this poset. Functions vary depending on the poset. Is it so the Mobius function? Maybe back at the Mobius function. It's some kind of and yeah, somehow something like the Mobius function. It has its own Mobius function. Say it again.
Thanks. So
we can check that this persistence diagram does satisfy the Mobius inversion formula. So for example, at the point 2, 6, we have a number 2. Well, the sum. How do I say this example? Yeah, let's do this. So here, quadrant, if 4, 6. If we do the points in this quadrant, we get 3, which is here at F diagram at 4, 6. Okay, let's talk about integer coefficients. So what I'm here is I do a sublevel set filtration, I apply coefficients. Then when I get a persistence module, what I'm doing is I'm going to the free part. So I'm going to forget the free part. So here I have a persistence module, and it's constructed 1, 2, 3, 4, 5, 5. And so at 2 I have C mod 2Z, over 4 I have C mod 4Z, over 6 I have Z mod 2Z. And the 4 is a multiplication by 2. Then 6 I'm just going to quotient by the image from 4. Okay, so I'm using the same procedure to describe the persistence diagram. I'm going to define a map DF, each interval to some element of a group G, and we don't know what this group G is yet. Look here. So what is we want to assign to it some group that captures the image from P just before Q. The first diagram of this thing will simply be the Mobius inversion of okay, in this category of finite abelian groups, and so group G is a deep group of this category. So here's the structure of the Grothendieck group. So I have this category of finite abelian groups. U is set. The set of isomorphism classes of finite abelian groups. And now this monoid, meaning it's an element because Z is a finite abelian group, and I can add stuff. So if I have abelian groups A and B, I get direct sum B. So it's not a group because it doesn't have inverses. So we have inverses. So I with a bar is a groupation of the set of isomorphism classes. But that's what we need. So in the fundamental theorem of finite abelian groups that says that every abelian group is isomorphic to something like this. So it's Z mod P1 to the power of Z plus, every is isomorphic to a sum of primary cyclic groups. So here, the K is a natural number, each is a prime number, and each is a natural number, a positive natural number. So this group is isomorphic to the abelian group generated by the set of pair gamma P. So in an abelian group, I can represent it as an element of this group. Right. Looking for some notion of a negative finite abelian group because we're not done yet. There's another step. Group I bar, and Q be the subgroup generated by the set of elements B minus C for each short exact sequence. C. When you have an abelian, when you have a sequence of the exact sequence need not split. Mean B may not be isomorphic to A plus C. This is for vector spaces, but not for abelian groups. Quotient out by Q, meaning we're going to force this. So we're going to force the B to be isomorphic to A plus C. So this category. You take these generally isomorphism classes of finite abelian groups, and you quotient it out by these exact sequences. For example, suppose you have a short exact sequence that looks like this. You have Z mod PZ goes to, so here. So if you have a primary cyclic group, Z mod P to the power n Z, into a short exact sequence like this. This group, that this primary cyclic group is going to be equivalent to m copies of Z. So it's equivalent to mod P is Z plus itself m times. So, and by Z for any P is a simple group, so you cannot make it up any further by a short exact sequence. So Turnian group is the Abelian group generated by the set of primes. Okay, so example again. We're going to have a procedure to compute its persistence diagram. I will call the dx in this diagram. So at point 4, what we do is look at the image in just before 4, which is Z2Z. We look at it just before we get to 6, it's Z mod 2Z. 6, so 2 to 6 image, 4 to 6. Before 6 is Z mod 4Z, but in this Grothendieck group, Z mod 4Z is get the element, gets sent to 2 copies of Z mod 2Z. And 8, 8 is Z mod 2Z. Inversion, the value of the persistence diagram at 2, 6, we do the same trick. We put square down. We do a plus minus thing. So it's going to 2Z, 0 plus 0 minus 0. We get mod 2Z. Here we square down again. For 4, 8, we get C mod 2Z, plus 0 minus 0. For 4, 6, we go to put a box down, and we computation again. So we have copies of Z mod 2Z minus a copy of Z mod 2Z plus a copy of Z mod 2Z, so we have 0. So that's the persistence. So far. Okay. So now, we have made a notion of persistence diagrams for finite abelian groups and faces. This is a metric between persistence diagrams. They're called erosion distance. So here's how it works. First, I define from the post dgm to itself, and what interval and grows it by epsilon. And then suppose we're given a persistence diagram P, and it's from dgm into G, non-zero and finitely many intervals. I'm going to E by epsilon. This means I'm going to compose it with grow epsilon. And so it's the picturing. So suppose P is the persistence diagram. So P is a diagram with 2 points, so 2 black points. And what it does is, well, first you draw a box of that. You draw a box on each point, and then you slide the black point to the lower right-hand corner. This point onto there. Can you guys see my cursor? Probably. This point is very close to the diagonal, so it's just going to disappear. What it does is it takes a persistence diagram and shifts every point by epsilon. And there's a morphism from a persistence diagram P to P prime. A morphism from P to P prime is the following relation. If I interval I in M and I do a sum, so I do a sum J containing I, that adds to the sum for P prime. Re-interval in DGM. The distance between P prime is a minimum such that the following. So if we have P and P eroded by epsilon, we're going to get this, there's this relation, just by definition of erosion. So there's P epsilon, there's a morphism from P epsilon to P prime epsilon to P prime. And yeah, erosion distance is the minimum epsilon such that these cross morphisms exist. This definition, it's a reasonable distance, if you've heard of that. Okay, so my density persistence diagrams require some partial ordering on the group. Vector spaces, so the category of vector spaces is Z. And so there's a ordering on Z. And there's also a natural partial ordering on the Grothendieck group of the category of groups. It's the following. So X and Y are elements of this group. And X is less than or equal to Y. The projection to a prime P of the projection of Y P, all primes P. Okay, stability result. So functions F and G will consist modules, constructible persistence modules from these things. F1 into vect, so a module basis of field functions. F2, these persist modules using Z, and then I'm going to forget the free part. So give the category of finite abelian groups. G. So if the F in G is at most epsilon, the interleaving distance between the two modules is at most epsilon, and this inversion distance is at most epsilon for finite abelian groups. In terms of proof, this theorem, so the second here, it's very it's a lot of improving bottleneck stability. And you can take a look in the paper. Yeah, so it's getting closer. And any questions?
Amit, question.
Yeah.
So a little bit about the relationship between the erosion distance and the interleaving distance.
Well, if the interleaving distance between two modules, F1 and Fg, is less than epsilon, then the erosion between the persistence diagrams is less than epsilon.
But not equal.
Not equal. I think should be able to construct. Yeah. 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 So in the case of vector spaces, there's isometry theorem that says that I think categories it's true, but for others it's not.
Cool.
Yeah.
Yeah.
I think vector spaces, yes, it's true. I think that's classically known, right? We all know that.
Huh.
Yeah.
Does erosion distance appear in your paper with Herbert and Dimitri? And you like a cold erosion distance?
Yeah,
you
it did.
proved that
Yeah,
was
it appeared a
equal.
while ago. So it appeared in the paper for Dimitri. We're trying to get distance for maps from the surface to the plane. Yeah, so that's where it appeared.
Mm.
So sign a persistence diagram for a constructible persistence module valued in any symmetric monoidal category with images. And there's some weaker notion of stability here, which we talked about in this talk, but there's some weak notion of stability. But there is abelian. Then there is no, not actually, there is in the paper I proved that there is one with stability with respect to distance. And another generalization that is not in the paper, inversion formula is well post set. So if you have a finite post set and a map to some abelian group with the partial ordering, you can do this inversion. That any constructible persistence module valued over a post set, constructible persistence module over a post set valued or has a persistence diagram. Special interest might be multidimensional persistence modules. Where you have more than one filtration simplicial complex. For example, here's my module. So you have simplicial complex, a finite simplicial complex, and you have two in something like a functor from a custom R2 to some category C, maybe just like bases to keep it simple. And that's something like a DF. So here the post set will be the category of rectangles. Have some rectangle, you can assign image from the lower left-hand corner to the upper right-hand, to the left-hand corner to the upper right-hand corner. There's some write that image as some element of the Grothendieck group of your category. Conversion. All the downsides to this way of thinking is that two more, for example. So if I have two functions and I collect a multi-D module, these are going to be very interesting. They're going to be curves and stuff, and that's not going to work. So I think if you have two functions of some complex, not.
Can I ask a question?
Yeah.
So DF here is you can think of that as sort of like the rank invariant. Is that right?
Yeah, exactly.
So so the persistence diagram that you build using the Mobius inversion, that's sensitive to the rank invariant. Is that right? So I think there exists multidimensional persistence modules that aren't isomorphic, but they have the same rank invariance. So
yeah.
Those would have the same. Yeah. Cool. Thanks.
And also, I suspect if you so this let's just say vector spaces, modular vector spaces, because of the wildness of this quiver, that like when you do this inversion, negative numbers in the persistence diagram, you might have rectangles with negative numbers. Huh. But I haven't worked that out, you know.
Thanks.
On work, Brittany facing an algorithm to compute the erosion distance. And it seems like distance, which we're excited about. Goes off. Is he here? A code that computes persistence over all fields, Z mod PZ at once. This be related to, so I'm trying to figure that out.
All right, great questions. Sorry, so can you, in the case where the code is just vector spaces, can you tell us, can you do the difference between bottleneck distance and erosion distance?
Yes, I've been working on this. So the bottleneck distance is, I'm going to screw this up. Are you there? One other, so yeah, the distance is less than distance. And we have an example where the two are different.
Yeah.
And that's spaces.
Because you've been but the inner, maybe not.
Yeah,
Yeah, it's less than interleaving. And interleaving is the same as bottleneck.
Yeah.
Okay.
Yeah. The distance is less than equal to bottleneck.
Yeah.
And then that shows that they don't have to be equal.
Yeah, I have it. So, I mean, most of these stuff is quite wild, and it seems like what you're having is related to the rank invariant.
Yeah.
Something is somehow between one persistence and multi-D is that zigzag persistence. A rank invariant is not invariant in a certain sense. I'm just guessing. I'm asking, what does your barcode construction look like for, or your persistence diagram construction look like for zigzags?
Yeah, I don't talk about that. That's different, yeah. Very different. Yeah.
But the difference in going from R to R2 than going from space where you have arrows in different directions. Yeah, I think you were talking about more general concepts.
Between,
I mean, it feels like what you're doing, like zigzag should fit in your framework somehow.
yeah, I'm working on with, yeah, this is a project with Bob McPherson. We're studying maps from striped space into manifolds. We want it there, so it's there. But, this for more persistence, this have here. This way of thinking is Mobius inversion. If your module is constructible like this grid-like thing I've drawn. The problems really quickly. Yes. Yeah, I do.
Okay. Thanks.
Well, if there are intelligent questions, hi everyone. This is Radmila. I was here because I'm teaching. I actually have a question. I'm sorry for my ignorance. So which Grothendieck group are you computing?
The group of an abelian category.
Split one or?
So you take the isomorphism classes, turn the group, and then you quotient out by the short exact sequences.
exact sequences. Okay. Okay, and can this be actually done for like different types of Grothendieck groups, right? So,
Yeah, this in the paper. There's two different types. There's a Grothendieck group of symmetric monoidal category, and there was you just do the first step. You take the isomorphism clauses and you turn that into a group, and that's the group of a symmetric monoidal category. I couldn't prove this one Lipschitz stability with that. So the extra step further, when you quotient out by short exact sequences, magically get one Lipschitz. Quotient out, you're losing a lot of information. So
I see. Is there a way to get like the ring structure on it? Like, would it make sense to see that?
yeah, I don't talk about that, but yeah. So I mean, in the abelian category, you can tensor things, so you can make it into a ring, but we haven't gone in that direction. Right?
I mean, it would be interesting to see what sort of gives on the level. Like, okay, I'll take a look how.
It's possible. You can do it. Yeah.
Okay. Thanks. Later discussion. Yeah.
So in the other case that you weren't able to prove stability, is that because you think it's not true, or because you just don't know? Okay.
Yeah.
Thanks. I think I'm it for a really nice talk. Thanks a lot.
Thank you.